Okay, so in this video, I'm going to talk a little bit about how you actually find pipeline schedules. So in the last few videos, we've talked about the effect of pipelining on performance and why computing a low initiation interval for a loop is critical for performance. But we haven't actually talked about how you figure out what the lowest legal initiation interval should be or could be. And we haven't talked about what limits initiation intervals. So in this video, I just want to go intuitively over a very simple example of how to find a pipeline schedule for this very simple loop. So here's a function, and the function is called sum. It takes in a pointer and an output, and then it sets a temporary variable. I forgot to put the int here, but should be int sum equals 0. And then for I equals 0, I less than 2, I plus plus, we're going to add I to the sum, and then we're going to write out 0 to be equal to sum. And if you're a compiler's expert, or if you just have some common sense about how optimizers work, you can tell that an optimizer could actually completely eliminate this loop. It could just optimize it away. But let's suppose that the compiler is dumb enough that it's not going to optimize it away, and just assume we're actually implementing this, this for loop right here, and trying to pipeline it as efficiently as possible. So, well, what does the assembly code look like, first of all? Because compilers don't really pipeline C for loops, they pipeline assembly code. So we're going to have three basic blocks, an entry block, a loop block, and an exit block. And we're going to set this temp variable to be 0, we're going to set sum to be 0, and then we're going to jump into the loop block. And then we're going to, in each iteration of the loop, we're going to set I to be equal to temp, so it'll initially be equal to 0. We're going to add I to the sum. Then we're going to set temp to be itself plus 1, and then we're going to branch. If temp is equal to 2, we're going to go back to the start of the loop and run the loop again. Or excuse me, if temp is equal to 2, we're going to exit, and if temp is not equal to 2, then we're going to loop backwards. And then in the exit, we're going to store the result to 0, or the 0th entry of out. Okay, so how do we actually find a pipeline schedule? So we've already covered straight-line code scheduling actually in the very first of the explanation of HLS videos. So how to schedule straight-line code like we see in the entry and the exit block is pretty straightforward. So how do we find a pipeline schedule for the loop itself? Well, if you remember what we've talked about in the different previous videos about pipelining and its effect on performance, a pipeline version of a loop is really two different things, right? It's an ordinary schedule like the one we computed in the very first explanation of HLS video, right, that basically computes start and end times for each of the instructions in the basic block. And then it's this extra variable, the initiation interval. And the initiation interval is basically the time between, not basically, it is the time between starts of successive iterations of the loop. So pipeline scheduling is really just like ordinary scheduling in the loop body, but we're also going to compute this extra value, the initiation interval, and we're going to try to make it as small as we possibly can to get the best performance that we can. And just to visualize this, we're really going to have two different things. We're going to have this red block, right, which represents the loop body schedule, and I've left it opaque, so because we don't know what the loop body schedule is yet, we don't know what the arrangement of instructions in it is. And then we're going to have some distance, the initiation interval, which is going to be an integer value between 1 and some number. And that's going to be the distance between starts of the loop. And the execution of the loop is going to look something like this, right? Just like we saw in earlier diagrams, we're going to start loop iteration 1 in cycle 0, and then II cycles later, we're going to start loop iteration 2, and then loop iteration 1 is going to finish, and then a little II cycles after that, loop iteration 2 is going to finish. So the question is, how do we compute the loop body schedule, and how do we compute the initiation interval? Well, here's a simple two-step plan, right? So first, we're just going to compute the ordinary basic block schedule that we would compute for any piece of straight-line code using a standard scheduling algorithm, just like the one that we talked about in the first few videos of this series. And then step 2 is the one that's still a mystery, and that's we're going to try to compute the best possible initiation interval for this loop. So let's just go through this plan for the really simple loop, just using our intuition and what we already know about basic block scheduling from earlier videos. So step 1 is pretty straightforward. We need to just find an ordinary schedule for this loop, where we set I equal to temp, add I to sum, add 1 to temp, and then check the value of temp and branch depending on it. And if you look at each of these operations, you'll notice this is an assignment, which in hardware just corresponds to connecting two wires. This is an add, which is a combinational operation, since it's an integer add. This is another combinational operation because it's an integer add. And this is an integer comparison, which is a combinational op. So all of the operations in the loop are combinational. So actually a combinational circuit that completes in 0 cycles can find a schedule for this loop. Or it can execute this loop, which means that an intelligent scheduler like the SDC, the Zhang scheduling algorithm that we discussed earlier in this series, should be able to figure out that actually the start and end time of every single instruction in the loop body can be 0, right? We can do this entire thing just by reading the values off of registers and that store temp and sum, and then updating the values, and then on the next clock cycle setting them. So all of the computation in the loop can be done inside of a single clock cycle. And let's suppose that the scheduler is intelligent enough to figure that out for us. And basically what this means is the body of the loop can be done with a combinational circuit. Okay, so what about step 2, computing the initiation interval? We know that we can design a combinational circuit that executes one iteration of the loop body, so what's the smallest initiation interval we can get? Well, first let's just use our intuition. If the loop finishes inside of a single cycle, well, we ought to be able to do it in one iteration, but what are the properties that could limit the initiation interval, and how do we figure out what they are? Well, first of all, again, let's just look at the intuition, right? Intuitively, here's what the schedule will look like, right? We can start the first iteration of the loop and finish it inside of a single cycle, and then because we've finished the loop inside of that single cycle, we can just do sequential execution, right? In the next cycle, we can just start loop iteration number 2, and that'll have an initiation interval of 1, and every loop iteration will completely finish before subsequent iterations, meaning that there's no possible violation of sequential data dependencies. Okay, so how do we get this out of the facts that we already know about pipelining? Well, here's a slightly more rigorous derivation of the fact that we can do an initiation interval of 1. So we want to get the smallest possible initiation interval, right? The smaller the initiation interval is, the better. The second thing is that, as we learned in the first videos about pipelining, no initiation interval can be smaller than 1, right? So the smallest possible initiation interval is 1, which corresponds to starting one iteration of the loop every single cycle. The other thing we know, and which we saw intuitively on the last slide, but which we also talked about a few videos ago, is that an initiation interval greater than or equal to the length of the loop body schedule is always safe because it corresponds to sequential execution, right? We talked about how there's a practical upper bound given by the length of the loop body schedule on the initiation interval, because even though you could make an initiation interval much larger than that, any initiation interval as large as the length of the loop body schedule is technically sequential execution, or looks like sequential execution. So it's also a fact that the length of our loop body schedule is 0, so actually any value that's greater than or equal to 0 would be a legal initiation interval, except that actually it doesn't make sense to have an initiation interval of 0 because the smallest unit of control we have is the clock cycle, and so really the initiation interval can't be smaller than 1. And as a consequence of this, we can see that the best possible initiation interval for this loop is 1, right? 1 is the smallest initiation interval that's legal, and it still respects all data dependencies in the program because it's effectively sequential execution. So hopefully that's pretty straightforward and makes sense. I kind of went over this almost in excruciating detail, this sort of argument. But I think it's important to just see an intuitive example and how the facts we've already learned about initiation intervals tell us at least a little bit about how to pick the initiation interval. Now, as you can probably tell, this loop is so simple that the fact that we can do the entire loop body inside of a single cycle makes the analysis of initiation intervals really, really simple. But the analysis is more complicated when the loop body is more complicated and takes multiple cycles to complete and possibly has data dependencies caused by operations, especially memory operations, which are particularly hard to analyze. So how do we do this kind of reasoning automatically, and how do we do it more precisely? That's the challenge we're going to look at in the next couple of videos, and what we'll do is, instead of using this kind of intuitive reasoning like we saw on this last page, which is sort of just a codification of the obvious, we're going to talk about how to actually examine the data dependencies across iterations of the loop, turn those into a linear programming problem similar to the linear programming problem we solved to do ordinary scheduling, and use that to compute the smallest possible initiation interval. So I'll see you guys in later videos where we're going to talk about that.